Nice. Okay, I see. So that's, yeah, this is basically like a CNC board, and you can move those wherever you need.
Yeah, it's just a smaller bolt circuit. That's all I'm doing.
Right on.
They call this a multi-site adapter. You know, basically put whatever you want on here. But the sweet spot's really set up for this center area. I'll show you on this film here while you're talking about it.
You guys have the PMA and
so you'll notice that we actually, here's our formula. We start in the center, we move out every half inch or so. But you can see that if you had a very large wafer and a small gun, your sweet spot's only so great. It'll fall off on the edges, so you can adjust the tilt. Right. So it really depends on what size sample you want to run.
What does the program tell you how long the test will take?
Well, it really depends what you're trying to obtain, and what do you use to measure films? Do you have a profilometer or?
What do you use to measure film?
Like the thickness?
Are you
talking about the thickness of the film?
Yeah, the size.
So, there's a lab upstairs that they have. It's not a spectrum. I can't remember what the name is called.
Okay.
They tap, they tap the surface at different points to kind of see, I guess, what the thickness is.
Okay.
I'm not sure what it's called, but we have one upstairs.
Yeah, so you know, we use what's called a step profilometer, and how we typically do it. If you have a metal film that's you know more than a couple hundred angstroms, I guess that's the threshold on that tool. You know, because it's not too accurate underneath that. But a couple hundred angstroms, we'll put what we call a deletion mark across the film. So we use Kapton tape. I don't want glass, you can use a Sharpie. Yeah. And then you peel it off, and then you measure the step height.
That's what we do with that.
I'm not going to put all these on. This is a pretty small sample.
And then you can check it. Yeah, then you can put like Kapton tape onto the glass slide, and you can put it on there, and you can take it off, peel it off, whatever.
So you notice it's kind of a horseshoe design. So there's two pins. Put this up, put it on, and you just gotta kind of wiggle it a little bit, it'll drop into place. Makes sense?
Yep.
Okay.
One sample, one
I'm gonna go ahead and close this.
Two small wafers per side is not possible.
Now I need to seal the door up. Would you like to try it?
Oh, the upgrade.
Yeah, you just have to hold on because it's on this curved cylinder, so it doesn't fly. And then just turn it, and you notice that this will seal up. You just have to close it till it just starts to get to an increase in tension.
So how big is the diameter of wafer you can use for this one?
For this one, that's a 6-inch holder.
6 inch.
Yeah. All right. And so the pump is.
We don't need to like put torque on it like a hatch.
No, you just need to put it down and just like lightly seat it.
Okay.
Because all you want to do is just compress that O-ring here, and then you're going to go back to your vacuum screen. I'm going to pump this, then I'm going to shut everything down and show you a cold start up.
Okay.
I want to show you the inside. Go over to PC pump. Click on it. PC's process chamber. It's loading the recipe. Go to this vacuum screen. This is where all the action's happening. So whenever we had the system vented, the turbo pump was still running. It was isolated from the high vacuum valve. The chamber was at atmosphere. So at this point, the turbo's still running, but it's not being backed. And the question I get asked, we gotta watch that too. I have a little cheesecloth over that. Yeah. So he first pumped from, you know, all this space. You're gonna get a bunch of vapors in here. But so I get asked, is it safe to run the turbo without it being backed? Well, in this situation, it is, because the isolation valve is closed, the high vac valve is closed, and This is your turbo backing valve. So there's a volume of about this much that it's pumping on. It's not getting a continuous gas load. So it can just sit there and spin indefinitely. So we're using the same pump, and now we're going through the roughing valve right here. So once we get to what we call our crossover pressure, which I believe is about 150 millitorr, we will turn off this here. It's been kind of foggy in here. turn that off. We'll turn the turbo backing valve back on. We'll have the system back. We'll check that this at speed light didn't extinguish, and we'll open the high vacuum valve. So right now, since the high vac valve's closed, we're reading off the convection gauge. So you notice as this decreases, it's showing in the wide range gauge. So we're at 120 torr. It's going to take a little bit of time. So you can do a few things. One, if you wanted to have a quicker pump down, we could reduce this line by about 5 feet, 6 feet. You may want to vent that outside.
Right. Yeah.
Put it in the closet, I don't know.
You were talking, yeah, Jaime and I were talking earlier about at least, I was going to get them a quote for oil mist eliminator filters for each one of the things, so at least they have
I just put a cheesecloth and a tie wrap on for now.
Yeah, that's good for today, but we'll definitely do better.
Please do.
So the preferred location for the vehicle to be installed on the there is center.
Yeah, center. Yep.
Now, my question is that if you have a regular shape of wafer, for example, you have semi-disc, so with a regular shape. So right now, how critical is that to make it at the center, because it's not physically possible.
Yeah, so with this 2-inch gun, you only have a certain focus of the plasma because of the size of the gun, and that's why with a 2-inch gun we qualify on a 4-inch wafer. So if you can be within 2 inches of center, you should be able to get this uniformity.
By 2-inch deviation.
Yeah, 2-inch left or right from center.
Okay, so that's also
2-inch gun, 4-inch wafer.
Correct.
You had
3-inch gun, 6-inch wafer.
now let me ask something else. If I divide a wafer disc into two semi-discs,
Yeah, so you scored it and
is
snapped
that
it.
possible simultaneously run it?
Yeah. Oh yeah.
Okay, so in this case we can have two or couple of wafer at the same time.
Yeah, I mean, yeah, as long as they're, on the, because whenever we sputter, we actually rotate.
Okay.
So it isn't static. We actually rotate it so you get even a distribution across.
Each one. You can have more than that.
Yeah, and the way your system's set up, you can run DC or RF, you can run them by themselves, you can co-sputter if you want. You can run 2 power supplies.
So we have two targets. This target is run by, one is by DC source, the other one is by, okay, so now what is the effect of these two sources on the deposition? I mean, for a specific application, we can use DC source or the other source.
Yeah, so I mean, typically metals are used with DC, oxides, oxides with RF. So metals primarily with DC because it's other than pulse DC, I don't think you can really sputter an oxide via DC. Yeah. So oxides are primarily used on the RF source, and that's actually a great question. I was going to get into it, but if you look up here for the sources, so you notice it says source 1 and then in parentheses it says RF right here, source 2 DC. So these tabs, they're not very distinguished. I mean, they're not very what's the best word? One's not as dark as the other, and sometimes they're a little difficult to distinguish. But if you highlight it, you notice that this is white and this is a bit of a off gray. This says RF, and if you hover over top of this, power supply 1 enable RF. So power supply 1 goes with source 1.
Typically, it goes from
Power supply 2
ship it.
goes with source 2. The pop-up is power supply 2.
So right now, so we are running source 2.
So you have, right now, you have aluminum in both.
Yes.
In both. So we can run RF in source 1. We can run DC in source 2. I think that's the way it is. Yeah. I can run aluminum co-dep.
So what material is preferred exclusively for RF?
For RF, basically oxide targets.
Oxide target.
Yeah, and I know that Warren brought that chart along. Warren, I believe on that chart, it gives preferred deposition techniques, RF DCs. Yeah, so you should be able to refer to that. It's a pretty good indication.
It's on our website too, all that information on that chart. Like if you go on our website and just look under the materials section, you can look up aluminum and it'll tell you, all that information and more. So.
What are you from? What are you on?
When you're done, you're gonna add some special effects and sound effects to that, right?
So we reach crossover pressure, and the high vacuum valve opened. When the high vacuum valve opened, they turned the filament on. Took a few seconds to turn the filament to light. Now we're reading the ion gauge within the wide range gauge pressure. So I'm going to do something here. I just want to kind of reinforce the conditions. So we're pulling down the vacuum. This is green. This is on. If I shut this off, ion gauge goes out. And we're reading the convection gauge. Now, I said earlier the convection gauge is good to about 1 on 4, but we're deeper than that. So we get what we call a nonsensical value. First it was 5 on 5.